From Photonics Media, this is All Things Photonics, a podcast where we explore industry-shaping advancements in lasers, optics, imaging, metrology, and sensing. Each episode, we'll speak with some of the brightest minds in industry and research about the trends shaping the landscape of photonics.
Today's episode is brought to you by Hamamatsu Corporation, a leading manufacturer of devices for the generation and measurement of infrared, visible, UV light, and X-rays. Hamamatsu is dedicated to the advancement of photonics through extensive research and offers specialized systems for select applications. Visit hamamatsu.com to learn more.
Conversations around free space optical communication have generated a lot of excitement, but not necessarily the same level of substance. While wireless communication has advanced rapidly over the years, in many ways, it remains tethered to optical fibers. Cutting the cord on these systems, free space optics can enable comparable speeds while transmitting data through light beams. An enticing option for individuals and businesses who don't have access to fiber, agencies trying to stay connected when disaster strikes, or companies that just want a backup in case their cable's cut. But free space optics still have some hurdles to overcome before it reaches the masses. That's where groups like Attochron come in. They are actively working to develop the next generation of light waves for free space optical communications. Using short coherence length optical sources, including ultrashort pulsed lasers, they're able to overcome some of the most common issues hindering these systems. On this episode of All Things Photonics, we'll be joined by Tom Chaffee, Attochron founder and CEO, Jim Olson, Senior VP of Sales and Marketing, and Wayne H. Knox, Professor of Optics at the University of Rochester and consultant to Attochron. In this conversation, we'll discuss the origins of free space optical communications, Attochron's position in this ever-emerging tech, and why these systems might be best implemented as a third point in a communication triad alongside optical fiber and radio systems. Gentlemen, thank you all for joining me today. I wanted to speak to your team because there's been a lot of buzz around free space optical communication. And I wanted to cut through the noise to see where we are in this technology. And Tom, can you tell me more about where this tech stands today and Attochron's role in this field?
So Attochron is the only company that has offered a carrier-grade free space optical communications technology. When I say that, what we're doing differently is we are using what's known as short coherence length optical sources, which is a fancy way of saying lasers. We could maybe just use the term laser to represent the optical source. All other companies, as far as we know, are using continuous wave lasers, which makes a lot of sense if it worked well in atmosphere. In other words, the world's fiber optic networks are based on the use of continuous wave lasers in fiber. And they tune the index of refraction of the fiber to be ideal for propagating, for beaming that laser through the fiber. However, the atmosphere is constantly changing its index of refraction in very short distances. So a continuous wave laser having a very long coherence length begins interfering with itself with the constant changes of refractive index.
To give an example about this, everybody has experience with mirages, right? And you can see what happens on a hot, sunny day when the ground is being heated by the sun, and you see all kinds of strange things, right? There's the story about the guy who's in the desert, right? And he's thirsty, right? And he sees this shimmering, looks like a lake in the horizon. He keeps going and going and never gets there because there isn't any, okay? So that's a way of thinking about what happens to a laser beam when it goes through the atmosphere. It's really getting bent by the fact that the atmosphere has difference of index of refraction. That Tom was talking about that before. So I think it's a good way to think about this. In the Institute of Optics, where I'm a professor, we have an expression for the students. We say, "Be the photon." Okay, this is what we tell the students: be the photon. So what we mean by that is you just pretend you're a photon going through the system. What happens to you? Okay, so now you think about this. The photons are launched from the telescope, right? They're going across a mile and a half, whatever the distance is. What are the possible things that can happen to that photon, right? It can go straight all the way through, and it can go into the receiver, and it can go bink, and you have a 1 or a 0 detected, right? That would be successful. But there are other things that could be happening. It could be raining, it could be snowing, it could be fog, it could be all of those things, which can scatter that photon and send it out so it doesn't get to the detector, right? So we're just being the photon and thinking, well, the interesting thing is going back to the mirage. Well, in a mirage, you can actually see where you think what you're seeing. You can see through there. The light is getting through there, but it's getting perturbed, right? So what's happening is the normally straight path of the photon is being bent in a kind of a random way. And we call it the squirmy worm effect, right? And so the photon is going along, and it's being almost like wiggled around. And what we realized was that as a result of that, a bunch of those photons in that beam, they may start off at the same time, but they're not going to arrive at the detector at the same time, okay? Because they've gone through different parts of the beam, they've gone through different parts of the atmosphere, they've gone through different index of refraction, so they get there at different times. So that's where all of a sudden we realized in Attochron that actually this opens up the possibility of different kinds of sources that we can use.
Attochron uses a short coherence length laser, and what that means is that the coherence length is shorter than the disturbances in the atmosphere, so the integrity of the signal remains. It's not totally immune, not totally perfect, but it does finally address the number one problem in telecommunications, which is commercial last mile. So quite literally right around a mile, but that signal has to be on par with a fiber optic signal or a radio signal. And that we have taken the quality of that signal from a continuous wave laser is not uncommonly 10 to the minus 3 bit error rate. So that's a 1 error in 1,000. We have taken the state of the art up to 10 to the minus 9 or above, which is an error in 1 billion. And that is where the carriers want the signal to be. We have also, by using the short coherence length or SCL signal, it also reduces scattering because it's avoiding this problem with the index of refraction, the constantly changing index of refraction. So you have a signal that is scattering less, which means it's putting more power on target, which means you can also focus more, if you intend to, focus more energy on target.
There's a very nice analogy with another field where there's been a lot of rapid developments. I think your listeners know a lot about this, optical coherence tomography, OCT. And you would know that in the really early days, pioneers like Jim Fujimoto, who was an expert in femtosecond lasers, showed you could use femtosecond lasers to do imaging, and did some astonishing imaging inside the eyeball using these femtosecond pulses. And if you looked at what the whole field, as it developed over years, people realized that, well, yes, you can use a femtosecond laser for that. And the femtosecond laser has a short coherence length. And really the coherence length is the thing that matters when you're doing optical coherence tomography. And so knowing all that and working with Attochron, I realized that it was, in fact, that when those photons arrive at the detector in different packets, different parts of the beam, that if it's a short coherence length source, then they don't interfere with each other. And that's a very, very important thing. And Tom had mentioned before that we believe that the real reason that the CW laser fails to perform properly under a wide range of conditions is because it has a long coherence length. And so those different parts of the beam, if you like, the different photons in the different parts of the beam actually do interfere with each other, and they give something called coherent interference. It's also known as multipath interference. That you see that in radar systems. They have these funny echoes that happen. Multipath interference happens in cell phone networks as well, radio systems. So again, this also occurs in multimode fibers. You have multipath interference. So again, I think that with these analogies, we can understand that that we actually have a wider range of sources than people realized at first, that really can be used to really move the needle and give much better performance.
Interesting. And continuing to talk about the laser choice here, how do you characterize the arc and the evolution of the notion of deploying femtosecond sources, ultimately short coherence length, as an alternative to continuous wave sources? Because like you said before, a lot of groups are going to continuous wave. But what is the essence of this, and the difference in concepts, and I guess the advantages, into the goals that your team is going after?
Well, let's say this. Let me start with this. In 1997, I conceived of the concept of using a femtosecond laser in free space optical communications. That was effectively unknown. It was inspired by the work the University of New Mexico was doing on behalf of the Electric Power Research Institute. Now they just call themselves EPRI. But EPRI was interested in conducting lightning strikes away from power plants. What the heck has that got to do with free space optical communications? Well, what it showed to me was that UNM was purposely beaming a particular kind of laser into the most inclement weather and being able to keep a channel open to conduct lightning. So while that might not be obvious and on the face of it, what that showed me was that there was a laser out there which could possibly beam telecommunications in the worst possible weather. And at that time, there was an explosion of free space optical, or FSO companies, and that was happening in parallel to fiber optic communications going in the ground. And in the mid to late 1990s, we had the proverbial .com boom, but the networks that were going to supply that internet and allow the connections to those internet companies was being put in the ground for the first time at scale, at a very large amount. So naturally, lots of people were looking and saying, hey, what's a way to avoid having to trench in the ground? And besides it costing money, taking time, permitting processes, and then maybe accidentally what you're going to run into when you're trenching under the ground, and then having to maintain that physical plant of a wire in the ground and keep people away from accidentally cutting it. So naturally, many companies were launching FSO companies. Some started with just LEDs over very short distances, but most went to the continuous wave laser. But I saw the potential of the femtosecond laser just from the sheer success that they were having beaming this laser through the inclement weather. Now, they were turning the laser up to very high power levels, and they were actually ionizing the air. And the original concepts were maybe to ionize a pathway through the air with one femtosecond laser, and then follow with another femtosecond laser with the actual communication signal in that tube, in that ionized tube. But that is not eye safe. But that was the general inspiration at first. And when the .com crash came, University of New Mexico and EPRI lost their appetite, as did 90% of optical telecommunications technology companies lost their appetite to continue in that very bear market, as many of us remember. So what I did was I purchased the rights. I continued the research, created the company Attochron in 2002. We got our first angel funding in 2004, and then we began work with the Stevens Institute of Technology, and then we continued on our own at the Picatinny Arsenal wireless testbed, and we definitively showed that we could see up to and possibly beyond, but in terms of the demonstrations we were doing at that point, up to 30 decibel improvement in propagating with approximately 100 femtosecond pulse width with about a 30 micron coherence length, and compared to a continuous wave laser that was matched in average power and wavelength, propagating side by side at the exact same time. So that's how it began. And then when we saw the absolute proof that this was such an improvement, that just kept us going to the point where We were angel funded for quite some time, and then private equity funded beginning in the beginning of 2016 by Three Cities Research Incorporated, otherwise known as TCR. And we began to build network modems, because not just propagation, just showing that the propagation is an improvement is that has to be there, and it has to be a massive change for the industry to be interested in it. But naturally, you have to show it as a proof of concept. So we had to build a network interface card that showed that we could put data on that signal or modulate that signal. And then we had to develop the receiver section, otherwise known as clock and data recovery, or CDR, that would handle a pulse that is absolutely discrete. Those ultra short pulses, those femtosecond pulses, come out as a totally discrete packet of light, unlike much of the optical communications, which is known as non-return to zero, which there is never, the light is never completely turned off. It is turned down for a certain number of bit periods to maintain the clock. But in the femtosecond laser, you are releasing discrete pulses with no energy in between them. So that clock and data recovery system has to continue to extract the clock without, and that's called true return to zero, or just return to zero, RZ, versus CW, which is turned almost off, which is called non-return to zero. It doesn't completely go to zero, non-return to zero. And so we had to develop a special network interface that was timed to the laser and not the network data coming in, because the femtosecond laser it does not listen to an outside clock. It is its own clock. It happens to be the most exact clock in technology, which opens up other possibilities as a time reference. But the point is that a separate network card, a separate receiver section, all of that had to be developed, which we did. And then we demonstrated that with the carrier Lumen in field and a Fortune 100 retailer. And now that product, now those technologies are desired in a product which we are bringing to market.
Interesting. And you talked about how discrete the ultra short pulsed lasers can be. Talk to me about how effective they are in other short coherence length optical sources, and mentioning how discrete they are, but how secure are these systems as well?
They're extremely secure. The beam of a free space optical communication system can be focused down to about 6 inches at a mile. We focus that beam down to an extremely small point. And that means that anybody trying to sniff that signal or intercept that signal is going to have to climb that tower. They'll have to climb up on top of that rooftop to try to intercept that signal. And once they do, there would be a significant disruption to the signal, so it can automatically shut off. Many of the other free space optical communications companies spread their beam out quite a bit. The purpose of that is to maintain pointing and tracking. So if a free space optical communication system is on a cell tower and it's moving around in different directions, and believe it or not, even on top of buildings, we've seen it could just be 3 or 4 or 5 stories tall. They're moving all day long. Now, that shouldn't scare anyone. I'm not talking about earthquake type movement. Just the slightest movement will push that beam off course if there is no automatic pointing, automatic tracking. So what Attochron is doing that is very unique is keeping that beam very focused to maintain a very high amount of available signal power. We've got every bit of 55 to 60 dB decibels of link margin. If the free space optical communications technology is spreading their beam out, if that company is using the technological approach of spreading the beam out to maintain that pointing and tracking, then that signal can be sniffed. That can be intercepted by others. So I believe our security is the highest of any free space optical communications link.
When we hear more stories today about free space optical communications, you think about bringing, or some, may read stories thinking about bringing internet or this kind of connectivity to a place that has not seen it before. When in reality, I think there are a lot of places, in very developed nations that you need to connect that last mile where fiber's up short. So there's a lot of excitement about cutting the cord. And, talk to me more about the potential for this advancement, and again, not just for those nations that don't have the access to the communications, but the ones that do, but just need to connect that last little bit where fiber, might be coming up short.
Well, the capability of free space optics allows flexibility for a number of key use cases. And we try to look at this from a market perspective, not just a technology perspective. So from a use case perspective, we've spoken about enterprise access, which is fundamental and basic, and cell tower backhaul. But there are many projects here that are talking about extending fiber out into rural areas. And by combining technologies, using fiber for the main core, extending out using free space optical communications, and then putting in radios, you can start to provision services in places that are underserved or not served today. But there are many other applications that are opened up as we develop both the light sources and the pointing and tracking. This could be everything from Earth to space or space to Earth for satellite communications. There's military applications that could be used, temporary installations in places where they're needed. You can use it for disaster recovery in places that have a disaster where the infrastructure, the fiber physical infrastructure, is impacted or destroyed, right? And you can also, from a carrier perspective, provision services much more quickly. Provisioning fiber is expensive, right? And it takes time, plus permitting and other things. For a carrier to monetize their backbone, they can bring optical services in more quickly to customers, and also provide what amounts to diverse routes into that customer to provide some level of resiliency for that enterprise network. So there's a number of applications that can be used. And I think as we deploy the technology, customers are going to creatively tell us what they need and how we need to deploy it differently. So what we're doing right now is scratching the surface with the technology, entering the marketplace formally, and laying a foundation for research and development to take this to places where, frankly, it has not been anticipated could be used before. We solved the two major technical problems that are there, but it's in the early stages of the light source and the pointing and tracking, which is absolutely critical for the success of the product.
FSO has always had this amazing promise, right? As this, I like to use the analogy of the third leg on the stool. If there's a three-legged stool and somebody's trying to sit on it to do whatever, play their guitar, milk the cow, whatever they're doing, it's tough when there's only two legs and you got to focus on balancing that thing. And we've got fiber optics as one amazing leg, radio as another amazing leg, but then this missing leg. And that has been the promise of free space optics, where you really see the nexus of wireless and optic, but not the replacement of either of the other ones. One of the things that we see that when people get what we're doing and get what's different, right? Because there's been so much smoke blown, so to speak, about free space optical communications because it is so darn exciting. The nation that does that first is going to be far and beyond any of its economic competitors. 10 million commercial last mile links are needed yesterday in the US alone. Vertical Systems, which is an excellent market research company in the telecommunications world, has clearly stated that I think it's 75% of small to medium-sized enterprises in the US have no fiber, will not be able to afford fiber. It's not that they can't afford to pay the monthly. They're standing there, they're ready to pay a 1 gigabit commercial monthly fee, which can be, single-digit thousands of dollars per month. They are ready for that. The problem is the 100,000, the 250,000, the $1 million it's going to take to trench that mile to them. So the biggest hole in commercial telecommunications is commercial last mile. Are there 100 use cases? Yes. Are there this handful of absolutely the biggest use cases in the world that need free space optics, that's really the punchline. I mean, it would be great to be able to bring a gigabit access to every village in a developing nation. And that's the sort of good works that a lot of people have been working on. But that doesn't change the economics of putting the fiber in the ground.
Today's episode is brought to you by LightPath Technologies. From concept through prototyping, volume production, and global distribution, LightPath has the optical and infrared imaging knowledge and manufacturing expertise to be your optics and thermal imaging solutions partner every step of the way. Visit lightpath.com to learn more.
Tom, we talked about kind of the smoke around free space optics in the past where, a lot of hype maybe and the substance kind of not there. And as a technology and as a commercial prospect, free space optics, its growth has not been linear, right? What has your experience in working in and on the periphery of this field been like over the last 25 years?
It's been an amazing journey. When we first saw our results very early on, comparing to continuous wave lasers, I thought that was a slam dunk. That was 20 years ago. Free space optics it's almost like a theme of a movie that couldn't be possible. Not in terms of its promise. Yes, the promise is amazing. People love lasers. And that stuff is great. But the fact that no one until now has solved the issue of maintaining a quality signal in atmosphere, even over what many people would consider a relatively short distance, 1 mile. Now, 1 mile happens to solve the biggest hole in telecommunications and is literally $1 trillion global opportunity. But that hasn't been done until just now with our technology. Not to go backwards here, but the dot-com bust cleared the deck of almost all of the free space optical communications technology companies that had launched in the late 90s and very early 2000, 2001. They almost all went out of business. There was another ramp in the late 2008, 9, 10 period, but then the real estate crash that really hurt a lot of them too, just because money was tight, money was expensive. And now here we are in the past 5 years where we've seen just a number of them launch. We have seen this dream, not only of free space optical communications, but I interpret it as a dream of countless scientists and program managers and financial folks that want to be the first to crack the code. This is one of those big things where, people work with radios, people work with lasers, and they've done fiber optic communications and they've done radio systems, and practically anybody can beam a laser through the air. But they can't get it to the point of making the product, to making something to demonstrate something that is that successful and accessible until now. I think one of the main things that I've seen are really two things: an undying devotion to try to make a continuous wave laser work in the air, defying physics, and a attempt to stop all others if it looks like if somebody else has a better idea.
So cables can be cut, right? You miss the dig safe, you go through it. Radio frequencies can be jammed. There's FCC requirements about keeping it up, but there are still hurdles to free space optics. So are these efforts enough to overcome the biggest hurdles that it faces now?
I think so. One of the discoveries that we made, because when people talk about free space optical communications, a lot of times they'll say, well, we don't expect to have much fog. We're not going to beam through clouds, so no problem. And there is a mistaken I don't know if the term is equivalency given to, if you can see through the air with your eye, with the human eye, that's what the laser is going to see. An infrared camera can see through the air at 1,550 nanometers. When looking through the air at 1,550 nanometers, it calls to mind what it's like for a human looking through water, let's say, maybe a 2-foot deep stream bed where you can't really focus easily on the stream bed, even though it's clear water. Why can't you focus on that? And that is a perfect analogy of, you see the index of refraction is constantly changing, so it's difficult to make out, well, those are the frequencies that the light is going to be traveling on the laser signal. And when it looks through the air on a clear day or partially overcast day, it is actually quite jumbled. And that is the real punchline, because what is the most common kind of weather? It's weather you can see through, because those changes in the index of refraction are happening more rigorously, more intensely when you've got a clear day, when you've got either partial cloud cover or no cloud cover. And so we might think, well, why is that happening? Well, if the sun is heating up the black tar road, the amount of the heat that comes up off that road is going to be more intense than off the white sidewalk. So you have all, that's just an example, and it's going to be different over green trees, and it's going to be different over rooftops. So you basically have the air constantly pumping, and that is helping to cause this problem of scintillation. Attochron, we had seen these results, the improvement over continuous wave laser. And you see on the left-hand side, it says SCL for short coherence length, because that actually covers femtosecond lasers and other light sources with a short enough coherence length, which are also covered by our patents. And then it shows continuous wave. And on the left, you see very clear rings, like rings of a tree, of that Gaussian power distribution. Most of the power is in the center, and you do not see the speckling that is on any kind of level that is like the image on the right.
When the coherence length, what Tom was just talking about, is the length over which the light can interfere with itself, right? And I was talking about this analogy with optical coherence tomography, and so I think that one of the good ways to think about it is that you need to have, the light has to be coherent with itself in order to give bright spots and dark spots. Okay, well, we call those interference fringes. Right now, Michelson knew this, and Michelson's interferometer in 1890. And A. Michelson was the first American to win the Nobel Prize in Physics for such a brilliant idea. But he showed that you could actually get white light to interfere with itself if you had the mirrors extremely close to each other. So over time, people realized that well, if the source has a longer coherence length, then that can be a little longer. But I think what we realize, and what Tom was just talking about, is now the fact that if the coherence length of the source is short, then it results in greatly improved noise statistics for the laser. And you know that the job of this machine is just to sit there and transmit a bunch of ones and zeros. You don't want it to transmit 0.1 and 0.7, and you want ones or zeros. You don't want anything that's not a 1 or 0 is going to be thought to be an error, right? And so the fact is that the best way to make this operate is to use a source and a system that has the lowest interference. And that you can think of, I talk about it as, think about the pepperonis on a pizza. Okay, right? Why not? Right? It's about lunchtime here. And we can talk about this, that the laser beam is the pizza. And the coherence patches are the pepperonis. Okay? Right? Just like that. And you can think about those pepperonis as being dropped onto pizza at all different times, right? They don't bump into each other. They don't interfere with each other. So I think that it's a very good way to think about this. It's also called, the theory is called Gaussian beamlets. You can think about them as overlapping, with each having different random phase delays, and have actually a new theoretical model that really shows this very nicely. We'll be publishing that soon. And that's work we're doing with some students also. So again, I think that we understand pretty well now what is the role of coherence, and the kind of things what Tom was just saying are clearly shown in those videos.
It's an interesting perspective that I have, having been at Terrabeam, which was a very well-run company in terms of leadership and direction and business focus. And it failed And the belief was that the kryptonite of each technology is out there, right? For radios, it's rain fade. For free space optics, it's fog fade. And jokingly, one of my customers said, and for fiber, it's backhoe fade, right? And which is a problem with cut fiber, and why it's not a universal solution for everything. So with that assumption, when I left TerraBeam, we knew that the promise that free space optical communications holds in the marketplace, it solves a major problem for service providers. And we knew it, but we didn't know what the problem was. Both Tom and Wayne had the curiosity to take this to a different spot. There's a lesson learned about technology here, with the assumption being that fog fade was the problem. Tom persisted for 20 years, longer than that, to try to solve the problem. And Wayne stepped in and understood the physics and the technology and explained it, which unleashes now the promise of the technology into the marketplace. So we're now making a conversion from a technology that people have typically not had faith in, but not really understanding why, and actually misreading the reason why, what the problem was, that it wasn't fog. In fact, it was clear air scintillation. But then going one step further and understanding the physics to be able to solve the problem. And that's where we are today. We stand on the precipice of being able to, one, understand the two problems that needed to be solved that had not been solved around the light source and the pointing and tracking. And then the second piece of it was to persist, to go forward and start to introduce that into the marketplace and convince people that all of that promise of free space optics can actually be realized.
Naturally, people will think intuitively, if they're not in the telecommunications space or they're not in the wireless telecommunications space, and they'll say, well, what happens if a bird flies through it? That is going to be not even noticed because of the fault-tolerant nature of the protocols that are being used.
Very generally known in the field of networking, I mean, or all of networking, is something called path diversity, right? And so you know that you could set up a fiber optic network in triangles or stars or different kind of metropolitan networks, where if there is a backhoe, as Tom was talking about, the fiber is cut, the signal automatically is lost, the system automatically redirects and goes to a different path. And everybody should remember that that's also possible with free space optics, that it is possible to take the same signal and transmit it to multiple places, and whichever one gets the best signal can give the best result, right?
And it's a technology that gives us the ability.
It's a very, very big bird. Right.
It is what you said, right, to solve some of the current problems that we're concerned of from a security perspective with, for example, undersea cable cuts. Right? To Wayne's point, how do you build a resilient network if the only cable that goes to a country is undersea and gets cut? So we have to have capabilities to think about the problems differently, right? Do you use free space optics as part of this to go to satellites, to reroute traffic to an endpoint if a cable gets cut? Because if that main cable gets cut, that country is cut off effectively, could be, from communications and key functions for that country. So look, we haven't solved the problem, but what we're doing is we're introducing capabilities that help us get there. And this is resilient networks is a key concept that service providers have to solve.
And I'll just mention on top of that, that in fact, the demonstration we did with the Fortune 100 retailer served three different purposes. One was that 25% of their stores, they're kind of an opposite. They're very aggressive in terms of their IT approach and their networking. So while the industry average is 75% do not have fiber and 25% do, they're an inverse of that. 75% of their stores have fiber, 25% don't. So why would they want us? Well, somebody could say, well, they want you for the 25% of stores that don't have fiber. That is the fact. But it turns out they want us for every store. And why is that? That's because they need a backup that they feel is just as secure as fiber, which none of the radio systems are, to run the point of sale data through all those credit cards. And in fact, their policy, when the local fiber connecting that store gets cut, is to automatically approve every single credit card, because it's either that or nobody is approved, right? That can get expensive very quickly, and it did for them on a couple of occasions. So in fact, they want redundant links that they feel are just as secure as fiber.
We've talked a lot about the potential from free space optics, and let's take a look into the crystal ball and see, where do we think this technology is going to play in our everyday lives in, say, 5 years?
That's a great question. Well, that Attochron is going to market in 2025 with low rate production, and then it will scale up based on market adoption. That's not a fancy way of saying we don't know. It's just there is such a dubious attitude towards free space optical communications from most, but we have all these tier ones, some of them which have been privy to coming on site and seeing that proof of concept that was happening. And we also have Fieldworks here in Lexington that have seen that. So their question is, how soon are you going to productize? Not does this work anymore? But there are others who have seen this sort of gathering of tier ones, and Lumen publicly declaring that they are buying Attochron equipment. So the plan is that we will get this low rate production, tens of links that we are building right now on our dime, and they will go to these prospective customers. Many of these people will get this low rate production link, be able to see how it works, and be able to say, okay, based on this performance and our network metrics, we know we can use 10,000 of them. We know we can use 5,000. We know we can use 100,000 of them. And then we really start turning the crank. So free space optics right here in Virginia, it's hard to believe there's 750,000 people with no broadband at all. How can that possibly be? Well, look at the Appalachian Mountains that come through the whole western side of Virginia. Trenching for fiber optics, that is a non-starter trying to get to those people. Trying to cover all those people with radio, yes, to put the cell site in the little valley, in the given valley, but how do you feed the cell site? Not with a series of a bunch of radios. They aren't going to scale the capacity over time, and you need to license all that wireless spectrum. So you would beam free space optics right to that cell site in that mountain valley, and then it is distributed via radio. It's distributed via existing copper wire or whatever the local infrastructure is. In 5 years, we could see, I will make a prediction when we're talking about the crystal ball. There's probably a very great likelihood that especially this new administration that's in Washington, D.C., is going to see the wisdom of free space optical communications being that third leg on the stool. You would be able to roll out that 5G network like originally imagined. So we see the potential of massive rollout of wireless networks as originally envisioned when 5G was fresh on the lips of everybody, and they painted all these amazing scenarios. I'll mention another absolutely amazing market vertical, Earth to space. That Earth to space connection, if that is provided as a reliable connection with laser, then it's assumed that the connection coming back down to Earth is going to be as reliable, maybe more reliable. We are confident that the Attochron source can be plugged into practically any optical ground station that exists right now if it is built for 1550 nanometer light, that we could plug our source into that and create the first reliable Earth to space and back, but Earth to space connection. What is supplying those satellites? If it has the free space optic around the Earth, wouldn't you want that same capacity feeding the satellites, because right now radio is feeding those satellites. So that's easily within 5 years. The rolling out 5G easily within 5 years. I'll talk about another market vertical, multi-dwelling units. According to Lumen, up to 90% of MDUs, multi-dwelling units in the US, have no fiber optic connection. That's hard to believe. That is the sort of thing that can be solved in 5 years. Commercial buildings could have optical capacity, and multi-dwelling units could have optical capacity. Rollouts can be within hours versus weeks or months, and permitting and causing ancillary problems.
Our roadmap is to focus on the basics. Tom just highlighted that just networking basics today have holes, and we want to fill those immediately. But it's around availability, right? Reliability, right? And basics of latency, right? Because these are what are going to drive. So you say, what drives then the development we have to do? It's going to be the customer applications. AI, quantum computing, and edge computing are going to drive things that are going to put demands on wireless technologies that can't be met today. Do we know how fast we can go into the future? We don't know, right? But the femtosecond lasers hold tons of potential.
The femtosecond laser can now be put on a chip, embody 100,000 wavelengths. So it's like 100,000 CW lasers. How many racks is that going to fill individually? This can all be part of one femtosecond laser, which they call an oscillator. All of those separate wavelengths are phase locked, which means they're not going to talk to one another. That's by the nature of the beast, which is a wonderful byproduct of a technology space. And you can run all of those channels in massive parallel processing on a chip. There is no greater economic value that I could think of any energy market, any telecommunications, any computing, in terms of the net effect of combining a femtosecond oscillator on a chip with massively parallel processing in an optical wireless. That is the future of telecommunications.
We have a technology evolution roadmap at Attochron that we've worked out that basically builds on all of that. And so that's the kind of thing that is, once the initial products are out there, there are really interesting scaling paths to adding more functionality, more capacity. And really, everybody normally thinks that if you want a terabit per second, you should use terabit electronics, but there really isn't any terabit electronics. You can do a lot with lower data rates, multiple channels, as Tom was saying. So I think that's probably a really, really good way to look at it, that there's these options that we have. It's just lasers. It's just optics.
Gentlemen, thank you so much for giving me your time to discuss free space optics and where it's heading. And I wish you guys all the best of luck going forward.
Thank you very much, Joe. We really appreciate the opportunity.
Yeah, and thanks to everybody who's on the call to listen. If you've got follow-up, certainly get in touch with any of us. We're happy to follow on.
Great talking to you, and shout out to all your listeners and readers. We here in Rochester love reading your stuff.
With that, we conclude another episode of All Things Photonics. Thank you to our sponsors, to the technical staff behind the scenes, and to continued support from the Photonics Media editorial team. As always, questions, comments, thoughts, and ideas are welcome. Let us know how we're doing via email at allthings@photonics.com. All Things Photonics is available on all major platforms and on our website, photonics.com.